This is Physical Chemistry, Chapter 17. We're starting Section 9 now. In Section 9, we're going to talk about the relationship between the equilibrium constant, capital K subscript C, and the rate constants, lowercase k subscript f for the forward rate constant, and lowercase k subscript r for the reverse rate constant, and for composite reactions. Now remember, for an elementary reaction, we showed a couple sections ago that the forward rate constant divided by the reverse rate constant is equal to the equilibrium constant. Now, we're going to make a couple of assumptions for now. One is that we have an ideal system. What this means in the case of whatever we're doing, kinetics, that gamma is 1, so the activity of a substance in the system is just equal to its molar concentration. And also we're going to be using the rate determining step approximation. Now let's look at this reaction as an example. This is a composite reaction that we're going to hopefully be able to analyze. So we have 2 iron 2 plus ions plus 2 mercury 2 plus ions in equilibrium, so we have a forward reaction rate and reverse, or forward reaction constant, reverse reaction constant, 2 Fe3 plus, and then just a diatomic mercury 2 plus. Now the Kc, the equilibrium constant, that is just going to be the products over reactions. So we have the Fe3 plus squared because of the 2, times the concentration of Hg2 2 plus, and then divided by the reactants, Fe2 plus squared because of the 2, and then Hg2 plus squared because of the 2. Now we're going to assume that it has this mechanism here. So reaction 1, that's going to be the slower step, or the rate determining step. We have 2 Fe2 plus 2 Hg2 plus in equilibrium. So we have K1 and K minus 1 for the rate constants here. 2 Fe3 plus 2 Hg plus. And then in the second step, we're going to have 2 of these Hg pluses from the first step in equilibrium with the Hg2 2 plus. And that's going to be the faster step. And notice the stoichiometric number is 1 for that equation. Okay, so I've talked about the same reaction as before. Since reaction 1 happens twice, remember, then the S is equal to 2. So it's that, with the 2's it's not an elementary reaction. With the 1's it's an elementary reaction. Remember, the nu in front of each species is the stoichiometric coefficient. The S in front of the whole equation is the stoichiometric number. So it's the stoichiometric number that we're ignoring. Okay, so from step 1, the forward reaction, the rate forward is equal to 1/2 times the concentrate, or the derivative of the concentration of the iron 3 plus with respect to time, equals 1/2 times the rate constant K1 forward, Fe2 plus, concentration of Fe2 plus times the concentration of Hg2 plus. And then just combining these two, we're going to have that's equal to Kf times Fe2 plus times Hg2 plus. Now, the rate reverse is going to be 1/2 times the derivative of the Fe2 plus with respect to time. That's equal to 1/2 times the reverse constant times Fe3 plus times Hg plus. So again, notice that when doing this, we ignore the 2's from the stoichiometric number, since that's not part of the elementary reaction. Now this Hg plus here is an intermediate, so we need to substitute out for this term, or that term. Continuing on this, finding the relation between rate constants and equilibrium constants. So from step 2 of that mechanism, we've got the concentration of the Hg2 plus divided by the concentration of Hg plus squared is equal to the forward rate constant K2 divided by the reverse rate constant K minus 2. So solving for the concentration of Hg plus, we get the square root of those two constants divided times the square root of the concentration of Hg2 2 plus. So substituting this back into the equation we had before for the reverse reaction, we get the rate in reverse is equal to 1/2 times the K minus 1 times this K minus 2 over K2 to the 1/2 times concentration of the Fe3 plus times the concentration of Hg2 2 plus, square root of that. So simplifying then this into just one constant, we get the rate in reverse is equal to the equilibrium, or the rate constant for the reverse reaction, times the concentration at Fe3 plus times the concentration of the square root. The square root of the concentration of Hg2 2 plus. Now remember, equilibrium, the rate forward must be the rate reverse. So setting those two equal to each other, we have the rate constant for the forward reaction times the concentration at Fe2 plus times the concentration at Hg2 plus is equal to the reverse rate constant times the concentration at Fe3 plus times the concentration of the Hg2 2 plus, square root. Oops, that's 1/2 power, square root. Okay, so just dividing then the Kf by Kr like this, we get Kf over Kr is equal to the equilibrium concentration of the Fe3 plus times the square root of the equilibrium concentration of the Hg2 2 plus divided by the equilibrium concentration of the Fe2 plus divided by the equilibrium concentration of the Hg2 plus. So you'll notice that's equal to the square root of the equilibrium constant. So another way to say that is that the square root of the equilibrium constant is just equal to, well, here's the rate constant, square root. So what that gives us is that if you have the rate constant for the forward reaction divided by the rate constant, the reverse reaction, this is the overall reaction, the composite reaction, it's equal to the equilibrium constant to the 1 over S for the rate determining step. Remember, S is the stoichiometric number for that equation, for that step. Alright, now we're in chapter 17, section 11. We're going to talk about unimolecular reactions. Now there are two kinds of unimolecular reactions we're going to talk about. Isomerizations and decompositions. Now remember, an isomerization is when you have a compound with one certain formula and it becomes a different compound with the same formula. So the atoms rearrange somehow. For example, here's isopropane. So it's obviously C3H6, and then you have a ring here. And then it can spontaneously turn into propene. It's still C3H6, but obviously it's no longer a ring. Now the energy of activation for this reaction is the 274 kilojoules per mole. And this, we're going to use this delta symbol here for the isopropane. So the rate of the reaction is going to be a constant, rate constant obviously, times the concentration of the isopropane. Now another example, let's say we have this methyl isocyanide. Notice that the nitrogen is on this first carbon. And then that can spontaneously turn into methyl cyanide. Notice we have the two carbons connected to each other in this case. The energy of activation for this reaction is 160.5 kilojoules per mole. Now a decomposition is when you have one molecule split into two smaller molecules. For example, we have, what is this? Chloroethane, and it can spontaneously turn into, what is this, C2H4, so I guess that's ethane, or ethene, plus HCl. The energy of activation of that is 360 kilojoules per mole. Now let's talk about the Lindeman mechanism to explain how this is possible. Let's say we're going to go from A to B in an isomerization, or let's say A to B and C for, some reaction. And we're going to talk about the gas phase for now, not that it really matters. Okay, so what we're going to say, we're going to use capital M to denote any third body in the collision. M, it could be another A molecule, it could be a product molecule, just a random piece of dirt. Capital M, we're going to use this to mean third body. Capital M can be any other object. It can be another A molecule, it could be a product molecule, any totally other molecule. So we're going to write it like this. A plus M going to A star plus M. What this means is that A and M collided. Some of the energy was transferred from M to A. So now we have A in an energized state. So A star means A with energy. Okay, so this is a physical reaction after this random collision between A and anything else. Now, there are two possibilities. One A star can collide with another M, or the same one, it doesn't matter. And then you get just A and M back, which means that A has lost its energy and nothing's happened. There's no net reaction. Another possibility, though, is that you have this A with the energy in it, the A star, that it's got enough energy to break apart into the products. In that which case you got this rate constant K2. So our overall reaction then would be just this bottom one, the A star, the energized state of A going to the products with rate constant K2. So we're going to write this, our rate is just the derivative of the concentration of B, that's our product with respect to time, and that's equal to this K2, rate constant, times the concentration of this A star. Now A star, of course, is like an intermediate. That's really what it is. It's a intermediate state between A having normal energy and none. So we're going to use the steady state approximation by saying, okay, the concentration of this stuff, A star, is constant. So we take these rate constants here and we write them, we set them all equal to 0. So 0 is equal to K1 times the concentration of A times the concentration of M minus K minus 1 times the concentration of M, A star, minus K2 times the concentration of A star. So what we're going to do now is we're going to solve for A star. So we can substitute it back in up here. Okay, so like I said, with the steady state approximation, we're assuming the concentration of this A star is constant. So we solve for A star and we get K1 rate constant times the concentration of A times the concentration of M divided by the reverse rate constant K minus 1 times the concentration of M plus the rate constant K2. Now we can substitute that back into equation 1, and we have R is equal to K2 times K1 times the concentration of A times the concentration of M divided by the reverse rate constant K minus 1 times the concentration of M plus K2. Now also, M is sort of like an intermediate. We're just using it as a source of energy. So we're going to assume that's constant by the steady state approximation, which is probably true anyway because it's not a gas or anything. I mean, it's not a reactant or product or anything necessarily. So all these terms over here are constant except for the concentration of A. So what we're going to do is just take all these other things and make it a new constant times K sub U and I for unimolecular. So Ku and I is equal to K2 times K1 times the concentration of M divided by the K minus 1 times the concentration of M plus K2. Or multiplying, dividing by, you know what I mean. You can rearrange that dividing top and bottom by the concentration of M, and you get K1 times K2 over K minus 1 plus K2 over concentration of M. Now, this concentration of M, remember, it means all other objects. So realistically what that means is the concentration or pressure of all species, including the reactants and the products. So look at what happens if this concentration goes to infinity, this fraction here goes to 0. So in the high pressure limit, this constant K unimolecular is just K1 times K2 over K minus 1. Okay, so in the same reaction we've been talking about, there are two limiting cases. So one is like I already kind of started to describe on the previous slide. If the concentration on the bottom, K minus 1 times the concentration of M, is much greater than K2, then we take all this, K1, K2, concentration of A, concentration of M, over K minus 1, concentration of M. We got rid of the plus K2 because we're saying it's small. And in that case, the concentration of M cancels out on both sides. So our rate law simplifies to just a constant times the concentration of A. This makes it a first order reaction. This is the high pressure limit. Now on the other hand, if this term on the bottom, K2 is much greater than K1 times the concentration of M, then we write the rate law. So now on the bottom we got rid of this K minus 1 concentration of M, and so the K2's cancel out. So then R is going to simplify to K1 times the concentration of M times the concentration of A. And you'll notice this is a second order reaction. So under low pressure, it simplifies to second order. Under high pressure, it simplifies to first order. Now that's not quite, it's related to how long the species A star is going to last. Now if we have the energized species of A star, is short, then K2 goes to infinity. What that means is then the A plus M is going to go back, it's going to become your products. On the other hand, if the A star lifetime is longer, then the A star is going to decompose into the, it's going to just go straight to the products, and that'll be first order. Notice the difference here. Continuing on physical chemistry, this is the last of section 11. So this is a graph of what we just showed here. We're graphing the unimolecular rate constant against pressure, increasing pressure here. I sort of drew this sloppy, but anyway, this is a straight line going up and right. The slope of this line, the value of the line is K times the concentration of M. So with increasing pressure, double the pressure, double the rate constant, basically. And then up here is supposed to be a horizontal line because it's a constant. It's just K1 times K2 over K minus 1. Now we're in physical chemistry, chapter 17, section 9. We're going to talk about the relationship between the equilibrium constants and the rate of reaction constants. So let's say we have an elementary reaction. In that case, we've shown that the equilibrium constant, Kc, remember C because of concentration, is equal to the the rate constant for the forward reaction divided by the rate constant for the reverse reaction. And like I said, this Kc is equal to the equilibrium constant. So we're going to assume for now that we have an ideal system. What that means is that gamma is 1, so that the activity of each species is just equal to its molar concentration. And we are also going to be doing the rate determining step approximation, just to simplify things for now. So we're going to look at this specific reaction right here. So we're going to have 2 Fe2 plus 2 Hg2 plus in equilibrium, so we have a forward rate constant, a reverse rate constant, with 2 Fe3 plus Hg2 plus, or Hg2 2 plus. Okay, more of physical chemistry, chapter 17, section 9. So for that same reaction, the equilibrium constant, remember, is going to be the products over the reactants. So we have the Fe3 plus squared, because of the 2 in stoichiometric coefficient, times the concentration of the Hg2, 2 plus, to the first power, because the stoichiometric coefficient was 1. Those are the products. And then the reactants, we have the concentration of the Fe2 plus squared, again, 2 because it had a stoichiometric coefficient of 2, times the concentration of the Hg2 plus squared, again, because it had a stoichiometric coefficient of 2. Now this is our proposed mechanism we're going to look at to see how it works out. So what we're saying is there's the first step. We're going to have 2 Fe2 plus Hg2 plus. Oops, I think I forgot a 2 there. Yeah, there must be a 2 there. Fix that. Okay, so 2 Fe2 plus 2 Hg2 plus in equilibrium. So for this elementary step, we're just going to say K1 for the forward reaction constant and K minus 1 for the reverse rate constant. And then 2 times Fe3 plus, or plus Fe3 plus 2 Hg plus. We're going to say that's our slower step. And so that's going to be our rate determining step, because we said we're going to use the rate determining step approximation. And then notice we have the whole thing multiplied by 2. It could have been 1, 1, 1, 1 for an elementary reaction. So we say that our stoichiometric number for this reaction is 2. And then the second step, we're going to take this 2 Hg2 plus in equilibrium with Hg2, 2 plus. So again, we're going to have equilibrium constants for this elementary reaction, just K2 for the forward and then K minus 2 for the reverse. And of course, the S stoichiometric number for this equation is just 1. Now, since we're actually doing this twice, this first step twice, this, the way it's written, is not an elementary reaction anymore. If we had 1, 1, 1, 1, that's your elementary reaction. So remember, the symbol nu is your stoichiometric coefficient. So, 1, 2, 2, 2. And then the stoichiometric number is whatever is out in front of the whole equation. Okay, continuing on physical chemistry, chapter 17, still in section 9. So that same example reaction. So now we're going to look at the first step of that mechanism, the proposed mechanism. So the rate in the forward reaction is going to be 1/2 times the differential of the concentration, the Fe3 plus. Remember, this is one of the reactants. With respect to time, of course, because we're talking about a rate. That's going to be equal to 1/2 times the forward rate constant for that elementary step, times the concentration of Fe2 plus, times the concentration of Hg2 plus. Oops, I think I got that wrong. That's one of the products, isn't it? Okay, right. And then, so this is going to be equal to the rate constant of the forward rate. Yeah, the rate constant forward times the concentration of Fe2 plus times the concentration of Hg2 plus. And then that same reaction in reverse is going to be 1/2 times the differential of concentration of Fe2 plus with respect to time, obviously. That's going to be equal 1/2 times the rate constant for the reverse reaction times Fe3 plus, concentration of Fe3 plus times the concentration of Hg plus. Now remember, when we wrote out this reaction, we had 2's in front of everything. But that's just because the stoichiometric number for the reaction was 2. But if you write it as an elementary reaction, it's 1, 1, 1, 1. So the stoichiometric coefficient is actually 1 for each of these. So that's why we wrote this up here using 1's, not 2's. And then for the second step, we got the concentration of the Hg2 plus divided by the concentration of Hg plus squared is equal to the rate constant of that forward reaction divided by that rate constant of that reverse reaction. Solving this then for the Hg plus, we get Hg plus is equal to the reverse rate constant divided by the forward rate constant, square root of all that, and then also times the square root of the concentration of Hg2, 2 plus. Okay, now in physical chemistry, chapter 17, section 9, we're still on step 2 of that example. Oops, I spelled reverse wrong. So now we have the rate constant for reverse, or no, the rate for the reverse reaction is 1/2 times the rate constant for the reverse reaction of that elementary step. Oops. Oh yeah, so we substituted that in, what we did on the previous step. So then we have K of the reverse reaction of the second step divided by the K of the forward reaction of the second step to the 1/2 power times concentration at Fe3 plus times the concentration at Hg2 2 plus to the 1/2. And then we can simplify that, combine all these constants to one constant called the forward rate constant. So we have the rate of the reverse reaction is just K times the reverse, or that should be multiplied, not equals. So the reverse rate constant times the concentration at Fe3 plus times the concentration at Hg2 2 plus. And that's the square root of this concentration. Now for equilibrium, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. That's basically the definition of equilibrium. The overall concentration isn't changing, so the forward reactions, reverse reactions all balance out. So we also know for an elementary reaction that the rate constant of the forward reaction divided by the rate constant of the reverse reaction is equal to the equilibrium constant. I think I mentioned that a couple slides ago too. So at equilibrium then, we know we can substitute in those two formulas we came up with and say, okay, the equilibrium constant of the forward reaction times the concentration of the Fe2 plus times the concentration of Hg2, or the Hg2 plus, is equal to the rate of the reverse, the rate constant for the reverse reaction times the concentration of the Fe3 plus times the square root of the concentration of Hg2, 2 plus. And then just doing a little division here, solving for the rate constants on one side, we have the rate constant of the forward reaction divided by the rate constant of the reverse reaction, and that's going to be equal to the equilibrium concentration, the Fe3 plus, times the square root of the equilibrium concentration, the Hg2 2 plus, divided by the equilibrium concentration, the Fe2 plus, times the equilibrium concentration, the Hg2 plus. And that's going to be equal to Kc, the equilibrium constant, to the 1/2 power. And the reason for this 2 is because that first step, the rate determining step, S was equal to 2. Remember, we talked about the stoichiometric number. This here is your stoichiometric number. Okay, continue on physical chemistry, chapter 17. This is the last of section 9. So previous slide we showed then that the rate constant of the forward reaction divided by the rate constant of the reverse reaction is equal to the equilibrium constant of the reaction to the 1 over S power. And S is the stoichiometric number in the rate determining step. Remember, we used the rate determining step approximation as well as several other approximations. But this is going to give you a formula for your overall reaction, not just an elementary reaction. Okay, continuing on physical chemistry, chapter 17. We're in section 11 now. So this chapter, we're talking about unimolecular reactions. There are two types we're going to talk about. One is isomerizations and one is decompositions. And here are a couple examples of isomerization reactions. So one, we have cyclopropane, CH2, CH2, CH2 in a really tiny tight ring. And then that can decompose, or, not decompose, isomerize into propene, CH3, CH, CH2. Notice these have the same overall formula. They're isomers of each other. And then, so this is cyclopropane, this is propene. The energy of activation of this reaction is 274 kilojoules per mole. So the rate of the reaction is just going to be a rate constant, K, times the concentration of your reactant, which is the cyclopropane, which we're just going to use a little triangle for now. And then another example would be the CH3NC, which is methyl isocyanide. And that can isomerize into CH3CN. That's just methyl cyanide. The energy of activation for that reaction is just 160.5 kilojoules per mole. Okay, continuing in physical chemistry, chapter 17, section 11. So here are a couple examples of decomposition. Let's say we have C2H5Cl. It can turn into C2H4 plus HCl. The energy of activation for that reaction would be 360 kilojoules per mole. Now another example would be HNO3 going to NO2 and then OH, radical, free radical. So NO2 is brown and then OH is a free radical. That's not OH negative ion, remember. Now, a unimolecular reaction then would be any type where you just have A, the reactant, going to B, and then also the product, and then possibly other products. You can have one or more products. Now let's talk about the Lindeman mechanism to explain how a unimolecular reaction is even possible. Now we're going to use the symbol capital M to mean any other molecule. Doesn't mean methane, doesn't mean metal. It could be anything. It could be an inert gas, it could be product, reactant. It just means any third body. Alright, continuing on physical chemistry, chapter 17, section 11. So remember, we defined what M is, so let's see how we put it to use. This is still the Lindeman mechanism. Everything on the slide is Lindeman mechanism. So the first thing you do is you have your reactant A, and it collides with M, which we said is just another third body. And there's a forward rate constant for that, K1. And you're going to end up with A star plus M. So really, this is still A plus M, but what it's shown is we've transferred some energy from M. This A star means A, substance A, but in a higher energy state. So this here is one elementary physical reaction. Now there's two possibilities after that. One, you could have this energized state A star collide with another M, and it's going to we're going to have a reverse rate constant, go back to A plus M. In other words, we're losing this energy we gained, and we're back to where we started. There's no overall reaction. The other possibility, though, is that you have this A star in the high energy 8, and before it has a chance to collide with another M, instead of giving off this energy to substance M, it's going to turn into either B or B plus C. And then there's another rate constant, K2, for that. Now, if this is an isomerization, it's going to just go from A star to B. One substance becomes one substance. Of course, if it's a decomposition, then that one substance is going to become two or more substances. Remember, there could be plus D, I suppose. I don't have any examples, but I don't see why not. So you'll get 2 or more if it's a decomposition. So the overall reaction then, we're going to ignore this equilibrium of A going up to A star and back and forth, and just look at the overall reaction. We're just taking this energized form of the reactant A, using rate constant K2, and then it's becoming our B and possibly C, depending on the type of reaction. So the rate constant is going to be the differential of the concentration of our product divided with respect to the differential of time. And that's going to be equal to our rate constant for the second elementary reaction, K2, constant concentration at A star. And this we'll call equation 1 for future reference, because we're going to be doing something here. So we're going to treat A star as an intermediate, because it has such a short lifetime. Remember, this is a high energy state, and that energy is eventually going to go somewhere, somehow. So what we're going to do, we're going to apply the steady state approximation to this reaction and see what we can learn. Okay, continuing on physical chemistry, chapter 17, section 11. So we're going to use the steady state approximation. So the derivative of the concentration of that energized reactant, A star, the concentration obviously, with respect to time, is going to be equal to the forward rate constant in the first step of the elementary reaction, K1 times the concentration of A times the concentration of M, and then we have that same reverse reaction, so we subtract minus K minus 1 times the concentration of M times the concentration of A star, and then we have that second elementary reaction, minus K2 times the concentration of A star. Now remember, this is plus because, hold on. Okay, continue on physical chemistry, chapter 17, section 11. So now we're going to apply the steady state approximation. We have that quantity, the differential of the concentration at A star with respect to time. Remember, A star is the higher energy form of the reactant. So we're going to take K1 times the concentration of A times the concentration of M, subtract the concentration of K minus 1 times the concentration of M times the concentration of A star, and then subtract K2 times the concentration of A star. So remember, this is plus because this is how we're making A star, and these are both minus because they're using A star to make something else. And we're setting this equal to 0 because we're going to use the steady state approximation. We're saying that A star is an intermediate, therefore its concentration over time will be roughly constant. At least not the very initial and end of the process. So we're going to solve now for the concentration of A star. That's just algebra, so I did it for you. Concentration of A star is equal to the rate constant K1 times the concentration of A times the concentration of M. Notice this addition down here, so we have the reverse rate constant times the concentration of M plus K2. Now we're going to take this whole thing and substitute back in equation 1 that we defined on the previous slide to use or apply our steady state approximation. So the rate of the overall reaction is going to be the equilibrium constant K2 times the equilibrium constant K1 times the concentration of A times the concentration of M divided by the reverse rate constant K1 times the concentration of M plus K2. So now we have a rate reaction that doesn't have an intermediate in the formula. Except, well, for concentration of M, our third body, this too we don't want in there because concentration M, it's our steady. We're going to get rid of this by using our steady state approximation. Again, because it's an intermediate. Okay, continue on physical chemistry, chapter 17, section 11. So, from the reaction before, everything is constant except for the concentration of A. So we're going to combine all this other constant stuff and call that the equilibrium constant for the unimolecular reaction. So KUNI is equal to K2 times K1 times the concentration of M over K minus 1 times concentration of M plus K2. Now there's going to be two limiting cases of what this can simplify to. So for one, let's say that this term here, K minus 1, times the concentration of M is much greater than K2. Well, if that's the case then, you're going to end up with getting rid of the K2 on the bottom. So it'll look like this. R equals K1 times K2 times the concentration of A times the concentration of M over K minus 1 times the concentration of M. In this case, you can just cancel out the concentration of M, and then you combine all these constants. So So you just get K times the concentration of A. In this case, all you've got is a first order reaction. And if you've got high pressure, this is the limit of what's going to happen under high pressure. It will look first order. On the other hand, again, looking down here, if K2 is much greater than this K minus 1 times the concentration at M, then what's going to happen, on the bottom, you're just going to have the K2. So you have the rate is going to be equal to K1 times K2 times concentration M times concentration A divided by the concentrate, or equilibrium, the rate constant, K2. Obviously, these two cancel out. So then you just have rate is equal to K1 times the concentration at M times the concentration at A. In this case then, it obviously looks more like second order. This is the limit of what's going to happen under low pressure. Continuing on physical chemistry, chapter 17, section 11. We're still talking about unimolecular reactions here. So, remember we showed on the previous slide how you can have a limit of first order in one circumstance or second order of the same reaction in a different circumstance. Now we're going to elaborate on that a little bit. Whether it appears to be first order or second order is going to depend on how long this intermediate, the energized state of A star, lasts. For example, let's say the lifetime of A star is very short. Then what that means is that the rate constant K2 is effectively going to go to infinity. So then it depends on the concentration of A and M going to B plus C. So that's second order, because the A star is not going to last very long. On the other hand, let's say that we have A star has got a non-zero, an appreciable lifetime, a significant lifetime. Then it's not. Then we basically have A star going to B plus C. And then this is a first order reaction. Now, we already showed before, I'm going to rewrite it a little bit. So the rate is going to be equal to K1 times K2 times the concentration M times the concentration of A over K minus 1 times the concentration M plus K2. And that's going to be equal to K unimolecular times A, concentration of A. We already showed that before. And then we said, okay, all of this over here, we're going to treat that as constant. We did that with the steady state approximation. So we have K unimolecular here. That's K1 times K2 times the concentration M over K for the reverse reaction in the first elementary step, concentration at M plus K2. Or if we just divide by concentration M by concentration of M, which is 1, remember, then we get K1 times K2 over K minus 1 plus K2 over concentration M. These two are exactly the same, remember. Okay, continue on physical chemistry, chapter 17. This is the last of section 11. So the limit as pressure goes to infinity of K unimolecular is going to be K1 times K2 over K minus 1. Since K2 over the concentration of M is going to go to 0 as pressure increases to infinity, towards infinity. Then the limit of pressure as pressure goes to 0 K unimolecular, it's going to be K1 times K2 over K2 over M. So the K2's cancel out, bring the M1, the concentration M up, and you get K1 as the concentration M at low P. So at high pressure, the observed rate is going to be K unimolecular times A, and that's just going to simplify to K times the concentration of A. So this is going to be first order. And then at low pressure, the observed rate is going to be just K unimolecular times A, which would be K1 times the concentration of M times the concentration of A. So that's going to be second order. So this is how it's going to look here. We have increasing pressure down here. At low pressure, we have first order or second order. At high pressure, we have first order. And then of course in between it's going to gradually transition, make the math lots of fun. Okay, continuing on physical chemistry, chapter 17, we're in section 12 now. Now we're going to talk about reactions of 3 molecules. That would either be called trimolecular or termolecular. Both of those terms are correct. So let's talk about iodine splitting apart into an iodine atom and iodine atom. So this is diatomic splitting apart. These would be free radicals, remember, but we'll get to that in a minute. Now, I'm going to explain why in a bit, but this cannot be a unimolecular reaction. So, take for example though, what if there was a third body here? So let's say we have the monatomic iodine plus another monatomic iodine. These are both free radicals. Plus the third body, M. And that'll give us I2 plus M plus energy. Remember, these two coming together you might expect to be exothermic or something, right? So it turns out, and then the energy of activation, normally it's positive. We're going to show why for free radical reactions it's closer to zero. It can actually be negative. So this energy given off by this exothermic reaction, it would be enough to break the bond. So think about it. You have an iodine atom, they come together, they give off energy. That's enough energy to break it apart again. And that energy has nowhere to go. So this M, we're also saying it's acting as a chaperone, basically to move stuff around. Now, for comparison, if we had the CH3 radical, two of those coming together, that would make a CH3, what is that, ethane? Now this doesn't need a chaperone, and the reason is because this is a much larger molecule. It's got 18 vibrational modes to disperse all that energy. Think about it. All this energy is going to be concentrated in that bond between the two iodine atoms, but here all that energy can be dispersed throughout the whole 8 atoms. So the energy gets spread out and it doesn't cause any problems. So, like I said, the energy of activation for a free radical reaction is roughly zero. It can actually be, I don't know if this is a record, but it can typically be about minus 17 kilojoules per mole, somewhere in there. And again, I already said this iodine is a free radical. And in this example, like I2 going to I plus I, this would be bimolecular reaction. Continuing on physical chemistry, chapter 17, we're still in section 12. Hopefully this formula looks familiar from before. So we have the derivative of the natural log of K with respect to temperature is equal to the energy of activation divided by the gas constant R times the temperature squared. That's absolute temperature, obviously. So if we have a free radical reaction, as temperature increase, the equilibrium constant is actually going to go down. Now the reason for this is actually kind of what we've explained before. At really high temperatures, these free radicals, they have so much energy that the reaction can't go forward. They'll just break apart again. So solving that for K, we get K is equal to A times E to the EA over RT. And so if you put in a negative number, see what that makes sense? Yeah, they have a negative energy of activation, so put that in, you get a positive number here. Well, yeah, anyway, get the idea. So conclusion, so this I2 splitting apart into I plus I, it requires a third body M. So that we're actually writing it as I, it should be I2. Oops. Okay. I2 plus M goes to I plus M. So the rate of the reaction is going to be just equal to equilibrium constant K here, obviously, times concentration I2 times the concentration of whatever third body M. So again, we have at the low energy state, we have the diatomic molecule I2. That's why the ion is diatomic, and then higher energy, the free radicals. So that's just showing that the free radicals are in a higher energy state than the diatomic molecule. Coming up next, now we're talking about physical chemistry, chapter 17. We're in section 14. We're talking about fast reactions now. Let's talk about reaction, hopefully you've already heard of it by now, water. You've got the H3O plus hydronium ions and OH negative hydroxide ions, and then recombining to make just 2 H2O. This is an extremely fast reaction. Now the concentration of the H3O plus is about the same as the concentration of the OH negative, which is about 0.001 molar. Now the half-life for this reaction is about 7 times 10 to the negative 9th seconds, or 7 nanoseconds, which obviously a very short amount of time. Now the K for this reaction is 1.4 times 10 to the negative 11 per molar per second. Remember, K can be very big or small, but it can't really be negative. Now, we're going to talk about relaxation methods. Relaxation methods is where you start with your system at equilibrium, and then you change something very quickly. One example is the T-jump method. T stands for temperature, so this is the temperature jump method. Now this won't work if you have a reaction where the change in enthalpy for the reaction is 0. But it can be endothermic or exothermic, just it can't be delta H equals 0. So if delta H were equal to 0, then obviously the equilibrium constant wouldn't depend on temperature, and there would be no point in doing this method. And a way of doing this, you can just take electricity and discharge it through your system, or you take a high-powered microwave pulse and add energy to your system that way to heat up the temperature. Okay, we're in physical chemistry, continue on chapter 17, section 14. So relaxation is the time after equilibrium is perturbed until equilibrium is reached again. Now the second method of perturbation would be the pressure jump method, P jump. So what we have is this sealed container here. On one side we have just reactants and they're at low pressure, and then on the other side we have just some inert gas at really high pressure. And then in between, you just have easily ruptured boundary, like a strong membrane or something. You rupture this boundary, the gas goes over here, it increases the pressure on your reactants. Well, increases the pressure, you're part of the system of the reactants, and that'll cause a really fast change in pressure for you to study how pressure affects equilibrium for your reactants. And then 3, the E-jump method, which is electric jump method. Now here you just charge up a really big capacitor with electricity, and then you discharge it, you have your solution, an ionic solution between charged plates, and then you discharge the capacitor right through your solution there. And then 4, just flash photolysis, add a lot of light to add some energy to your system. Okay, continue on physical chemistry, chapter 17, section 14. So now that we've perturbed our system, we can talk about the kinetics of relaxation. So let's just talk about the easy reaction, A in equilibrium with B. So we have a rate constant for the forward reaction, a rate constant for the reverse reaction. Obviously this is first order for both directions. So the derivative of the concentration of A with respect to time is equal to minus Kf prime times the concentration of A. We're just going to say prime because this is our original equilibrium. Plus Kr prime times the concentration of B. And this is at any certain temperature. Now at equilibrium, we know that our overall concentration of A is with respect to time is going to be equal to 0 because we're going to be making it at the same rate we're using it up. So again, we're using prime because we're still before our perturbation, immediately after our perturbation here. So we have the minus Kf prime times the concentration of A prime plus Kr prime times the concentration of B prime is equal to 0. So solving, just getting these on opposite sides, we have the forward rate constant prime times the concentration at A, equilibrium prime, is equal to the reverse rate constant prime times the concentration of B at equilibrium prime. And this is for our original system before we perturb it. So now we're going to do the T-jump method. We're going to increase the temperature suddenly. So then we're going to change our Kf prime becomes just Kf, and our Kr prime becomes just Kr. And then now we just have the forward rate constant times equilibrium concentration of the reactants is equal to the reverse rate constant times the equilibrium concentration of the products. And this is our new equilibrium right after our perturbation. Now in physical chemistry, chapter 17, section 4. So at time equals 0, we have the initial concentration of A, 0, is equal to A, initial concentration of A, equilibrium prime. And then, so the equilibrium concentration at A, 0, minus the equilibrium concentration at A at equilibrium is just going to be X. This is 0. So the concentration at A minus the equilibrium concentration at A, we're going to call that X. And the equilibrium concentration of B minus the equilibrium concentration of B at equilibrium, by conservation of mass, we'll call that minus X. So we have the differential of the concentration of A with respect to time is going to equal to minus the the rate constant for the forward reaction as the concentration of A, plus the rate constant for the reverse reaction times the concentration of B. Now we want to substitute for concentration of A and concentration of B. Now we know the concentration of A is going to be the equilibrium concentration of A plus X, so that's our perturbation.
and then the differential of the concentration of A with respect to time is going to equal minus the forward rate constant times the equilibrium concentration of A plus X plus the reverse rate constant times the equilibrium concentration of B minus X. Just distribute the constants and we get the differential of the concentration of A with respect to time is equal to minus the forward rate constant times the equilibrium concentration of A minus the equilibrium rate constant times X plus the reverse rate constant times the equilibrium concentration of B minus the reverse rate constant times X. Now we know that whenever we're at equilibrium that the forward rate constant times the reactants are going to be equal to the reverse rate constant times the products. So we're going to use this and substitute back in up here. So we get the derivative of the concentration of A with respect to time is equal to the minus the forward rate constant times the equilibrium concentration of A minus the forward rate constant times X. And this is where we substitute it. We have plus the forward rate constant times the equilibrium concentration of A at equilibrium, yeah, I said equilibrium, minus the reverse rate constant times X. Okay, continuing on physical chemistry, chapter 17, section 14. So we have the derivative of the concentration of A with respect to time is equal to minus the forward rate constant times X minus the reverse rate constant times X. And let's just factor out the X. So we get minus the forward rate constant plus the reverse rate constant, both of those times X. Now we also know from before the concentration of A minus the equilibrium concentration of A, that's what we defined as X. Now we're going to write the differential of the equilibrium concentration of A with respect to time minus the differential of the equilibrium concentration of A with respect to time is equal to dx dt. Now remember, oh no, I see we took the derivative of this with respect to t. Well anyway, the equilibrium concentration is not going to change over time, so this term becomes 0. So we just have dx over dt is equal to d concentration of A dt. So using this, and this, we get the derivative of x with respect to t is equal to minus kf plus kr times x. Now this is a differential equation, but differential equations isn't a prerequisite for this course, and luckily you don't need it in this case. All we're going to do is we're going to separate the variables over here, or not, well, you know what I mean. Get the like variables on each side. So move the x over here and dt over here. So we get dx over x is equal to minus kf plus kr dt. Now we can integrate this because we have our variables separated, how we say it. So for x, we're going to integrate from our x naught to x, and then for time, we're going to integrate from 0 to t. And of course, we can pull out the constants. So we get the integral from x naught to x of 1 over x dx. That's equal to minus kf plus kr times the integral from 0 to t dt. Now this, of course, just becomes t, and the integral of 1 over x is natural log of x. So we get the natural log of x over x naught is equal to minus kf plus kr times t. Continuing on physical chemistry, chapter 17, section 14. So taking e to both sides of that, we get x is equal to x naught times e to the minus kf plus kr times t. Lowercase t is time, remember. Or delta x is equal to delta x naught is equal to e to the minus kf plus kr times t. Now tau is our relaxation time. 1 over tau is equal to the forward rate constant plus the reverse rate constant. So we get x is equal to x naught times e to the minus t over tau. Or delta x is equal to delta x naught is equal to the minus t over tau. Now all this we've been doing the past few slides, remember, this was an example for a first order reaction, one elementary reaction. Now relaxation time, tau, is the amount of time it takes for the concentration, this difference, A minus A equilibrium, which we defined as x, to drop by 1 over e, remember e is the natural number, about 2.718, of its initial value, which was x naught.
Okay, continue on physical chemistry, chapter 17, section 14. So, like I said, that was all for a reaction that was first order. Here's another elementary reaction. Now we have A plus B going to C with forward rate constant K1, reverse rate constant K2. Then 1 over tau is going to be K2 plus K1 times the concentration of A plus the concentration of B. So first order reactions, the relaxation time, it does not depend on the concentration. But for for higher order reactions, the relaxation time is going to depend on the concentration. Now, the application of the relaxation time, like we said at the beginning of this section, is to find the rate constants. Here's an example. Let's say we have tau of 2.0 microseconds when the concentration A and the concentration of B are each equal to 1 molar. But then we have a tau equal to 3.3 microseconds when the concentration of A and the concentration of B are each equal to 0.5 molars. Now from this, we're able to find K1 and K2. On the next slide, I'll show you how. Okay, we're going to cover two methods of solving for K1 and K2 based on the data we were given. Now the first method is graphical. You'll probably find this easier if you don't like doing mathematics. So here we've got 1 over tau for the vertical axis, and then the concentration of A plus the concentration of B for the horizontal axis. So even if you only have 2 points, you just do those 2 points, connect the dots, and extrapolate it to the y-axis here. So your slope is going to be K1 and your intercept is going to be K2. Now remember, K's, they're always positive, rate constants. Now, remember, we had this formula, 1 over tau is equal to K2 plus K1 times the concentration of A plus the concentration of B. Well, that's just y equals mx plus b, except we switched around the order on yours. Y equals b plus mx. So this is an easy way, even if you only have 2 data points. All right, continuing on physical chemistry, chapter 17, section 14. The second method is to find K1 and K2 given that information. It's just to solve simultaneous equations. Now, linear algebra isn't a prerequisite for this course, but that's okay, you don't really need it anyway. So we have our 1 over 2.0 times 10 to the 6 seconds. Notice we converted it from microseconds to seconds. That's equal to K2 plus K1 times 1 molar plus 1 molar. And then we have 1 over 3.3 times 10 to the 6 seconds equals K2 plus K1 times 0.5 molar plus 0.5 molar. So we have 2 equations, 2 unknowns. And like I said, even if you haven't had a linear algebra, you'd probably figure out that K1 is equal to 2 times 10 to the 5th, and K1, no, K1 is 2 times 10 to the 5th, K2 is equal to 1 times 10 to the 5th. And your K equilibrium, remember, is your forward rate constant, or no, is K1 over K2. Yeah. So forward rate constant by reverse rate constant is 2. So notice from our relaxation time, we were able to find K, the equilibrium constant. But you can't go the other way around. If you have your equilibrium constant, there isn't a way to go backwards and find the relaxation time. Continue on physical chemistry, chapter 17. Now we're in section 16. We're going to talk about catalysts in this section. A catalyst is any substance or species that speeds up the rate of a chemical reaction without being consumed. Now here's a graph to explain how a catalyst works. So we have our reaction coordinate here. So we have reactants over here, products here, and it's showing energy. So here we have the reactants up here, the products down here. So obviously this is an exothermic reaction. And then this hump up here, this is called the activation energy, or energy of activation. Now this solid curve just shows what happens if you go from reactants to products without any catalysis. As you can see, it can do it as long as you overcome this huge activation energy. Now if you use a simple catalyst, simple reaction, what it does is it creates a different pathway for the reaction to occur, but with a lower energy of activation. So you have your reactant, you only need to add this much energy to overcome that hump and get to product instead of this much. Having lower energy to overcome means, of course, your reaction is going to happen faster. Now, of course, it can be more complicated. Like, let's say you have a catalyzed reaction, but there's going to be like an intermediate step. You can have a couple different humps here. Like this would be your intermediate, and this would be the hump to get from
the reactant to the intermediate, and then from the intermediate to the product, etc. But we'll go into the details of that in just a bit. Continuing on physical chemistry, chapter 17, we're in section 16 now, talking about catalysts. Now, remember I said a catalyst, it doesn't technically change the energy of activation. What it does is it creates a new pathway, and that new pathway has a lower energy of activation. So in this section, we're going to be using some abbreviations for brevity. We're going to use capital R to mean any reactant, and then capital P to mean any product, and then capital I to mean any intermediate, and then capital C to mean any catalyst. You probably figured that out from the graph on the previous slide, but we're going to be doing that throughout the whole section here. Now, to understand the difference between an intermediate and a catalyst, remember, an intermediate does not exist at the beginning of the reaction. An intermediate is created during the reaction. A catalyst does exist at the beginning of the reaction. For example, here's a pair of reactions here. We're going to take a reactant plus a catalyst, so these are already there, and that goes to an intermediate, so we're creating the intermediate plus product 1. And then we're going to take our intermediate plus reactant 2, and that's going to give us product 2 and our catalyst back. So if we add these up, you'll notice that both the intermediates and the catalyst disappear, so that some people find it difficult to tell the difference. Just remember that, like I said, you need the catalyst at the beginning, and the intermediate is created somewhere else. Remember, these are in order, 1 and then 2. Now, then in biological systems, the name for catalysts, we call those enzymes. But for non-biological catalysts, transition metals, like in your catalytic converter of your car. I think that's palladium or rhodium, something like that. Continuing on physical chemistry, chapter 17, section 16. Now remember the equilibrium constant, Kc, is not normally affected by a catalyst. Think of the formula we learned before. We have delta G naught for a reaction is equal to minus RT natural log of Kc. Now we know that delta G naught is constant for any reaction as long as we're at a certain temperature. So if this is constant, this is constant, this is constant, this must be constant too. What the catalyst does is it changes the forward rate reaction and the reverse rate reaction. It changes both. The ratio, it stays the same. Because think about it, it lowers the activation energy. If it's lowering the activation energy for forward, it must be lowering the energy of activation backwards too. Can't really do one without the other. Now, just to refresh your memory, then the catalyst, it gets added in and it comes back out. So, on the other hand, the intermediate, it is produced and then used up. Now, homogeneous catalyst, it's the catalyst and the reaction mixture are in the same phase. For example, if we do the hydrolysis of ester, everything is in the liquid phase, so it's homogeneous. On the other hand, a heterogeneous catalyst, this is more important than industry, and that's because the catalyst, the reaction mixture, they form more than one phase, usually 2 phases. For example, let's say we have C2H4 plus H2 with a nickel catalyst, and then we get C2H6. That's all. Continuing on physical chemistry, chapter 17, we're in section 16 now. So here's that same reaction I showed you before. We have what is this, ethene in the gas phase, plus diatomic hydrogen in the gas phase. We run it over some metal, nickel solid, and PT, I guess that's platinum, palladium, yeah, probably platinum solid. Anyway, whatever it is, C2H6, that's ethane gas. So this would be an example of a heterogeneous reaction. So this is hydrogenation because we're adding hydrogen. And this takes place on the surface of the catalyst. We don't really have time to explain why it works, but anyway. So a catalytic converter, like in your vehicle, I think I mentioned that before. So inside your car engine, you have incomplete combustion. So instead of giving off just carbon dioxide and water, you've got some weird stuff like carbon monoxide and then NO2 because of the nitrogen in the air. These are all gases. And then the catalytic converter of your car, you have this rhodium. I forgot to write it down, but obviously this is a solid. And then that converts it to carbon dioxide and N2, which of course is a lot safer to breathe. And then although A catalyst, it cannot change the equilibrium constant Kc. I think I mentioned that 3 times already. It can actually change the resulting mole fractions because it can actually change, just by being in there, the interactions, it can change the activity of each species. So make sure you read carefully to the specific reaction of what you're doing to know exactly what can and can't happen, what will happen. Now there's also another word you need to learn, autocatalytic. This basically means the product acts as a catalyst. So the product is going to speed up your reaction. So look carefully at this reaction. We have ester and ester, just to be generic. R means, we're not doing reactant now, R means, what is it? Well, carbon, anyway, plus H2O. So and then we're going to catalyze that with acid, just H+. And then that's going to give a carboxylic acid, plus alcohol. So think about it. You're making an acid, but acid is a catalyst. So the more acid you have, the more catalyst you're going to have. So that's why this is an example of an autocatalytic reaction. Continuing on physical chemistry, chapter 17, section 16, there is such thing as a negative catalyst or an inhibitor. In a negative catalyst, these substances, they decrease the rate. There's a couple different ways this can happen. One, they can just destroy a catalyst, so effectively reducing the rate that way. Or two, they can react with reaction intermediates. For example, let's say you have this CH3 radical and you're trying to make a nice big polymer, but then you have this NO radical. Then, of course, you add these two radicals together and you got a stable molecule. So, well, relative. Nitrosulfide-methane. Now this .NO, this has very complicated chemistry, but like I said, in this case, what happens is you're inhibiting your ability to make polymers out of your organic molecule. Okay, continue on physical chemistry, chapter 17, section 19. Now we're talking about nuclear decay, which is the same as radioactive decay. This is always first order kinetic, and this happens because the nucleus is unstable. So you start out, we know that if capital N is the number of nuclei, so the change in the number of nuclei is going to be minus over time. They're going to lose them. They're going to decay. So it's going to be minus dN over T is proportional to the number of nuclei. And so what we're going to do is we're going to introduce a proportionality constant to make this, turn this proportion into an equal sign. We're going to use lambda and call that the decay constant. But be careful, it's the same symbol as wavelength, but obviously we're not talking about wavelength in this case. So then we have minus dN over dt is equal to lambda n. Now we're going to integrate both sides. Obviously we had to get separation of variables first. So the left side we're going to integrate from NO, the initial number of nuclei, to the final number of nuclei of 1 over ndn. And that's going to equal minus lambda, that's a constant we pulled out, and then integrate from 0 to whatever time dt. So that just gives us the natural log of the number of nuclei divided by the initial number of nuclei is equal to minus lambda times t. Then we take e to both sides and solve for n. We get n is equal to the initial n times e to the minus lambda t. Alright, continue on physical chemistry, chapter 17, section 19. We're talking about radioactive decay. So we take that equation, we're going to multiply both sides by lambda. We're going to define A is equal to lambda n. We're going to call A the activity, and then so A naught would be lambda times n naught. So that, multiplying both sides by lambda, we get lambda n equals lambda n naught equals e to the minus lambda t. And then substituting these in, we get A is equal to A naught times e to the minus lambda t. So lambda turns out to is 0.693 divided by t1 half. t1 half is the half-life, and 0.693, that's an approximation of the natural log of 2. Because it's, well, I'm not going to show you the math, but that's to get 1/2. So the activity reported is going to be in disintegrations per second, or just dps, that's the unit. So remember, if we have this nomenclature here, x, a, z, x is the symbol for the element, like H would be hydrogen, He, helium, etc. And then A is the mass number. That's going to be the number of neutrons plus protons. So Z, that's the atomic number. That's the number of protons in one atom. And then N is the number of neutrons. So A is equal to Z plus N. Continue on, Physical Chemistry, Chapter 17, Section 19, more about radioactive decay. So why are some isotopes radioactive? It actually depends on the ratio of the protons to neutrons in the nucleus of the atom. For example, let's say we have carbon-12, it's got 6 protons, and carbon-13, it's got 6 protons, and carbon-14, it's got 6 protons. All three of these have the same number of protons, but we've got 6 neutrons, 7 neutrons, 8 neutrons. This one's stable, this one's stable, this one's radioactive. Now let's talk about beta decay. What's that supposed to be a capital B here? Beta decay. So we have carbon-14 is going to decay into nitrogen-14 and give off an electron and an electron antineutrino. So the net ionic equation in the context of nuclear chemistry, basically, you've got a neutron, it splits into a proton and an electron, and then of course that electron antineutrino. Continue on Physical Chemistry, Chapter 17, Section 19, we're talking about radioactive decay, we're talking about beta decay still. So a beta particle, it's written like this, 0, -1, 0. So this a beta particle is the same thing as an electron, except it came from the nucleus when a neutron broke down. So a beta plus particle, that's 0 + 1, 0. That's the same thing as a positron. Positron is the same thing as an electron except for the charge. It's got a positive charge, just like a proton instead of a negative charge. Now beta and beta plus, these are antiparticles.
All library laptop computers are due 15 minutes before closing. If you have a laptop...
Okay, continuing on Physical Chemistry, Chapter 17, Section 19. So we're talking about beta decay still. So beta particle is written like E -1, 0. Because a beta particle is the same thing as an electron, except that it comes from the nucleus because it came from when a neutron in the nucleus disintegrated. Now, beta plus particle, that's written the same way, except we have E +1, 0, and that's a positron. Now, that's the same as an electron, except the charge. It's got a +1 charge instead of a -1 charge. A beta particle and a beta plus particle, these are antiparticles. Now, in nitrogen-12, it's got not enough neutrons. So what it's going to do, it's going to go from nitrogen-12 to carbon-12, giving off a positron, same thing as a beta plus particle, and an electron neutrino. So the net reaction is that one proton is going to become a neutron and a positron and an electron neutrino. Okay, continuing on Physical Chemistry, Chapter 17, Section 19, now we can talk about alpha decay. So let's say we have uranium-238, it's going to give off a helium particle and become a thorium atom. So this He2+, that's an alpha particle. It's the nucleus only though, 2 protons, 2 neutrons, no electrons. The half-life for this reaction is 4.5 billion years. Now an alpha particle, like I said, is 2 protons, 2 neutrons in a package, no electrons. Only the heaviest elements give off alpha particles. Obviously, a hydrogen atom could never give off one of those. So uranium-238 is actually, like I said, it goes to thorium, etc., etc. Eventually, it's going to end up becoming lead-206. Now, branching decay is when you can have more than one possible type of decay. For instance, polonium-218, it can experience either beta decay or alpha decay. So that's called branching. And that is all we're doing for Chapter 17.